Hi everyone, I'm Paula, and today I'll be introducing DELUCA, a new differentiable control library I've been working on together with John, Daniel, Alex, Naman, Uday, Karan, Cyril, Professor Majumdar, and Professor Hazan at Princeton University and Google AI Princeton. The two initial goals that led to DELUCA's conceptions were: one, to address the shortage of libraries that allow for auto-differentiation through simulation dynamics for the tasks most relevant to the reinforcement learning and control communities. By this, I'm referring to tasks such as pendulum, carpal, etc. And two, to facilitate benchmarking new advances in non-stochastic control, a new gradient-based paradigm which has led to promising preliminary results. As a starting point, we focus on basically adding differentiability to OpenAI Gym control tasks. Since we inherit their wildly popular interface, adjusting to the DELUCA is very user-friendly. As you can see in these two code snippets right here, interacting with the two libraries is basically indistinguishable. We hope this will make it quite easy for people to migrate from OpenAI Gym to the DELUCA in case they want to try out the differentiable counterparts of OpenAI Gym. We believe that this is a general important direction since most current simulators and algorithms are designed for discrete formulations of reinforcement learning tasks and hence disregard differentiability. While this is unavoidable, of course, for setups such as Atari and Go, there are many other physics based settings where this is highly suboptimal. For example, in the absence of true derivatives, policy gradient approaches estimate gradients by adding random spherical um, perturbations to policies, has incurring both avoidable error and computation time proportional to the dimension of the policy parameterization. While the popularly employed reinforced trick can remedy this policy space dependency, it relies on the use of stochastic policy, thereby introducing further variance in the problem formulation. For many setups, it would make much more sense to stick with a deterministic policy and therefore avoid this extra penalty. Some concrete algorithms which benefit from differentiability are, first of all, basically all policy gradient methods. This includes PPO or TRPO. Secondly, more typical continuous control planning algorithms such as the iterative linear quadratic regulator and model predictive control variants, since these leverage first or higher order approximations of the dynamics iteratively. And thirdly, non-stochastic control algorithms, a new set of methods that are inherently gradient based and which have been getting increasing popularity and promising theoretical and experimental results. Finally, we also believe our library will inspire future algorithm research that focuses on harnessing differentiability. So perhaps there's still a lot we haven't even seen yet, but that hopefully the Luca will help bring about. So we have decided to precisely quantify the expected speedups mentioned previously through experimentation. More specifically, we measure oracle complexity by looking at the number of calls to the environment's dynamics function in two different settings. First, we compare the convergence of ILQR on the planar quadrature task when using auto-differentiation versus when using finite differences to compute the stepwise linear approximation. This you can see in the first graph right here. Secondly, we compare the convergence of policy gradient on the inverted pendulum task with the typical swing up goal when using a deterministic gradient versus when using a zero order gradient, which you can see in this second plot right here. So we can see in both of these graphs that the availability of a true gradient vastly improves convergence rates for the two settings considered. And this corresponds to the suggested theoretical intuition. In the second case, the algorithm also requires a lot less hyperparameter tuning. In addition to these more theoretical speedups or sample complexity type speedups, we also enjoy purely computational performance gains. In this table right here, we compare the wall clock running time of the OpenAI Gym pendulum tasks with its replica in our library DELUCA. We timed both initial startup times and simulations with over a million time steps with input set to 0 so as to isolate confounding control factors. We see that at the cost of a one-time startup compilation, the improvement in per iteration time is greater than 1,000. This improvement arises from compiler optimization of functional loops due to JAX. So, on the large scale, especially for cleanly written, for functionally written code, DeLuca is actually noticeably faster than the established counterpart OpenAI. To motivate the value of our library to the research community, we also exemplify two particular use cases of DeLuca. One first exciting use case, which is concurrent work by our group, was tackling the task of mechanical ventilation. To do so, we first trained the neural network lung model on exploratory artificial breathing data and then added it to our collection of differentiable environments. Then, we were able to easily train a neural network controller due to the availability of auto differentiation through system dynamics. As a result, we were able to create a controller that vastly improves upon the industry standard of proportional integral derivative control. In the graph below, we can see that the new deep controller exhibits much smoother and more desirable behavior. Without differentiability, this procedure would have required significantly more data and resources. We believe that this is an incredibly exciting application, and we're excited that this differentiable library approach has enabled us and hopefully will enable a lot many other research groups to tackle such problems more effectively than previously. A second use case that has motivated our library was to benchmark classical and new control methods. Therefore, our library comes with both more typical control algorithms such as linear quadratic regulator or age infinity, as well as with new methods in non-stochastic control. With the Luca, one can easily benchmark new methods on either nonlinear tasks such as pendulum or in more typical setups such as linear dynamical systems. Furthermore, our library makes it very easy to see the impact of user-specified system noise on performance, something which we believe has been underexplored up to date but could potentially be of interest. Graphs such as the ones right here are very straightforward to obtain with DeLuca, so we hope that this will motivate increased empirical validation of theoretical working control. In order to achieve all of this, we make use of JAX, a new research library for automatic differentiation through native Python and NumPy functions. For neural networks, we use Flax, a neural network library built specifically for JAX. As mentioned at the very beginning, we model our API on that of OpenAI Gym, adding a side effect-free dynamics function with corresponding Jacobian and Haction functionalities. But the basic interaction with the environment through step remains identical. And we also return the same type of observations, rewards, and information. Finally, let's look at the current state of our library. Our currently supported environments are Cartpole, Pendulum, Acrobot, Mountain Car, Quadrotor, Linear Dynamical Systems, and two lungs, a physics-based one and a neural network-based one, which is the one I've discussed previously in the first use case. We can see that we've already migrated the entirety of the popular OpenAI Classic Control Suite, as well as added 4 other new environments of potential interest. But we're still continuously working on expanding this list. Currently available agents can be split into 3 categories. First, we support the classic control algorithms such as proportional integral derivative control, linear quadratic regulator, iterative linear quadratic regulator, and age infinity. Secondly, we support new non-stochastic control methods, which I will not go into, but feel free to look up at the citations right here. Finally, we support generic neural network controllers, trainable via policy gradient. In the video on the right, you can see a visual comparison of two of our agents, ILQR and AdaGPC. AdaGPC being one of the most advanced non-stochastic control methods that has just recently been developed. To recap, today I've introduced DELUCA, a new open source library with fully differentiable environments. Our library enables easy benchmarking of differentiable reinforcement learning and control. To facilitate this, we also provide pre-implemented control suite with both classical and new methods. Finally, we hope that DeLuca will provide an avenue for future algorithm development. So please check out our GitHub repository at this link right here. We hope that you'll find our library useful and perhaps that you'll even be motivated to contribute your own environments and algorithms. We'd we'd really like for this to become a big community-wide effort to move towards differentiable environments and algorithms. Thank you all for your time, and looking forward to questions during the workshop. Bye bye.
Okay, so I've got all the authors here, and I also have a bunch of questions. I'll just call out on the author and ask them questions, and they could respond. In addition to this, there may also be questions on Rocket Chat, which I'd encourage you to respond to right after this live Q&A. So the first question for Flow is, in your simulation control slide, you introduce a predictor network. And how do you prevent this observation predictor network from selecting trivial states as solutions?
Okay, we use this predictor network to kind of allow the network to look further into the future, and we pre-train this with actual simulation data. So we simulate reference data, and on that data we can train this prediction network already, and then reuse this in the optimal control. And so you can just do a normal supervised loss for matching physical states there.
That's good. So we have a question for Paula on DeLuca. To what extent are these simulations differentiable? For example, do we get gradients with respect to all plausible contacts and stuff?
So for now, we do have more simplistic forms of environment. So most of our state progression, the state progression can be modeled to a differentiable function. So you can take most straightforwardly derivatives through that.
Okay.
Yeah, you will get the Jacobian, and so you'll have a derivative with respect to the state and the action at any time step.
Sounds good.
And then you also have Hessians. And generally, everything is written in JAX and made to be a JAX object. So actually, you can basically call gradient on anything you can imagine within our library. It's just we focus on the aspect of differentiating through the system dynamics.
Sounds good. So I have a question on the body dynamics paper. It should be for Dan, I guess. Did you try and compare with open source projects like OpenPose on your work?
Yeah, so we haven't yet compared ourselves with things like OpenPose or like forward simulators like OpenSim. We did compare ourselves with different tracking algorithms that have some, spatial and temporal constraints. But the thing we cared about most isn't just the quality of the reconstruction or the simulation, but actually the identity of the physical quantities in any moment of time. We wanted to get the inertia and to get the fictitious forces and get this whole inverse dynamics quantities. So I wasn't aware that another method can accurately infer these from noisy joint positions. But yeah, I'll be happy to learn more about that.
Thanks. I think the next question is on the HDR paper. Is that Jung-hee?
Yeah.
So what sampling strategy do you use for sampling pixels, and can this method be improved somehow?
Yeah. For sampling, we use crossbar sampling method for getting the pixel values from the multi-exposure stack. And I guess there can be more efficient or way to get the samples, but because we gather all the values for 0 to 255, so I don't think other like method could much improve the total HDR consumption structure performance. Yeah.
That's good. Yeah. So we have a question on the blend shape paper, and it is, how do you actually choose facial landmarks, and will a poor choice of landmarks impact the output? Have you assessed some of that?
So first question, how we choose the landmark? There is the FACS system. So we manually decide the landmarks on the blend shape according to the FACS system definition of the landmarks. And for the second question, can you please repeat?
Yeah, it's about do a poor choice of landmarks impact your output a lot? Like, do the landmarks have to be very carefully handcrafted, or I think what it means is if you chose something else, would your results vary drastically?
Okay. Yeah. So because originally the blend shape can be considered as the dense mesh that can accurately capture every detail of the facial muscle of the deformation of the facial skin. But in our workshop, in our current work, we just use the landmarks to measure the deformation of the geometry. If we use other measurements, or if we directly use the whole dense mesh, there will be more accurate. These are the more accurate measurements of the deformation. So we expect the improvement of the performance of our top-down model if we use this dense mesh or other measurements instead of the landmarks.
Yeah, sounds great. Thanks. I have another question, I think, on body dynamics. This is great work. Can you give us an idea of the types of problems that this might be applied in? The mouse model seems quite useful.
Yeah, so this whole statistical kind of mechanical project came about through the actual neuroscience application. So our collaborators from the Costa Lab at Columbia, they're recording from the motor cortex of a mouse while it's performing some sort of reinforcement task. It's controlling the joystick, and they're recording from several populations within the motor cortex. And one question that arose was, what is actually the mechanical quantities that are being controlled and tracked by these motor and neurons? So imagine that in addition to the stuff that I've shown you here, we have time series of, say, of neurons in different brain regions, and we would like to regress them with these mechanical quantities and say, well, this population cares about the end effector pose, sort of a high-level representation of behavior. Where do I want to go as an agent? And another population may control the torques and the low-level sort of muscle commands. So it's a description of like biological motor control.
That sounds very cool. And yeah, it's a new dimension to this workshop altogether. So in the interest of time, I'll just take one more last question. And yeah, of course, I guess you'll have a lot of opportunity to chat about in the post session as well. So this one's for Paula, like about DELUCA. Do you plan on extending the suite of simulations to other physical phenomena like soft robots or fluids? I guess there's just about next steps.
Yes, yeah. So that's our main plan, to basically extend to more sophisticated simulation environments. I think for the beginning, we'll still focus on tasks that are fully like that we expect to be like that are differentiable inherently. But then the plan is to evolve, and maybe even consider harder setups.
Sounds great. So yeah, with this, I'd like to thank all of you for joining in and for taking time to answer questions.